Okay, good morning, everyone. Welcome to lecture 3. So before we get started, are there any questions on the first two lectures? Have you guys been attending the discussion labs? Awesome. So I think as some of you might have seen, so we have posted homework 1 on Canvas. So it's going to be due in 2 weeks, 2 weeks and 2 days to be exact. Friday the 29th. So please get started early. It covers today's lecture, material from today's lecture, and should be mostly straightforward, but it's always helpful to get started early because you would be coding some of these things that we would discuss today from scratch. So always good to have a head start, okay? Yeah, any questions so far about the material or about the logistics? Great, so maybe we can get started. So today, as you all know, like we're gonna be covering item set data. So in the previous two lectures, we got an overview of the different types of data that we will be studying in this course. And from now, this week onwards, we would be delving into great details about each of the data types that we learned in the first 2 weeks. And we would see some important data mining questions that you can ask based on that type of data and the methods to solve those type of questions, okay? First, some administrivia. So as I just said, for those of you who came a little late, so homework 1 is out today on Canvas. So please have a quick look and come to our office hours, come to the discussion labs, and it's always good to get started early, right? And it's due in about 2 weeks, so the Friday the 29th. Yeah, so let us know if there are any questions as and when you get started. So the homework is typically in the Jupyter notebook, where we ask you to write code for some questions and then explain why you made that choice. So you have to write your explanation as well as the code in the same Jupyter notebook, and that's what we will grade. Okay. Great. So let's get started with item set mining. So last week, if you remember, we talked about different types of data mining functionalities, right? We talked about classification, regression, ranking, and so on. And in the end, we concluded that although they might seem like numerous number of data mining functionalities, but in the end, it boils down to two main type of decisions that a data miner wants to make. And those decisions are based on patterns and similarities, right? So it's all about finding patterns, like the examples that I gave, that this basketball player has so-and-so physical attributes, or attributes of the game, or similarity. So-and-so person is similar to so-and-so on this particular game, and that's how we know they would be as good or maybe a little worse than that player, right? So today, when we will study item set mining, we will also study like how to find patterns in item set data, as well as how to find similarity in item set data. Okay. So before we proceed, can anyone remind me what was the item set data? Like give me some real world example of item set data. Yeah. Yeah. So items in the grocery cart. That's a great example of item set data. So let's see what is a pattern. And this is just a revision of what we studied last week. So pattern is a structure of attributes that represents some intrinsic or extrinsic characteristics of data objects. Okay. right? So think about it as characteristics of some type of data. Now, for item set data, a pattern can be a frequent subset of items. It could be an association rule, or it could be correlation of two items. Okay. So, as was just mentioned, so item set is a collection of items, right? So it's an unordered collection of items. We do not care about which item you put into your grocery cart first. We just care about whether it's there or not. So it's like a binary thing. Either that item is there or it's not. And we also don't care how many times you added it. So if you added 5 cartons of milk into your grocery store, for the item set representation, it would still be 1 milk, right? So it will not be repeated 5 times, okay? Great. So now let's, for item sets, since the name suggests, like item sets is a set of collection of items. It's like a set of items. So let's see some of the set operations that you must have studied in your like linear algebra class. So for two item sets, two collection of items, x1 and x2, if every item in x1 is also in x2, right? So then x1 is a subset of x2, and then x2 is a superset of x1, right? So just to give a concrete example, if we have a set 1, 3, 4, 7, 9, 12, okay, then 4, 9 is a subset of that because both 4 and 9 are there. We don't care what order they are in, or like whether 4 comes first or whether 9 comes first. We just care about whether it's there or not, right? And conversely, 1, 3, 4, 7, 9, 12 is a superset of 4, 9. Okay? So now, what is a frequent item set? For a frequent item set, first of all, let's think about what's a k item set. A k item set, so this is some notation that we use. So k item set is nothing but a collection of k items, right? So for notational purposes, we assume that in your shopping cart you have k items, okay? So for frequent item sets, like we use this term support, right? So support of an item set is the frequency of x in the database, right? And support can both be absolute support or it can be relative support. So absolute support would be number of transactions that contain x. If you're looking for relative support, it could be a fraction of items, or the percentage of items that contain x. And then we conclude that an item set is frequent if its support sup x is no less than a threshold, min sup. And this min sup is just a user-defined threshold, right? So as a data miner, like you would define, it's a user-tunable parameter that you would define that in order for an item set to be frequent, this is the threshold that we should have, right? And you could use domain expertise for that. So for example, if you are in a music store and you want to think of a collection of CDs, you might want to have a different threshold for min sub, but if you're in a grocery store, there might be a different level, a different value for min sub that you might want to have for your data mining problem, okay? So now let's go back to our shopping baskets, and let's look at some concrete examples of how to calculate support. So here are 5 shopping baskets from a grocery store, and they have some combination of beer, milk, watermelon, lollipop, cookie, bread, and wine. Okay, so people purchased some subset of these items. So now, what's the support of beer? And the answer is 80%. Could anybody explain how we got that 80% number? Based on what I said on the previous slide?
The number of beers over total items? Relative to the
Total transactions. Yes. So beer occurs, so there are 5 total transactions, and beer occurs in 4 out of them. So it's 4 divided by 5, 0.8 or 80%. And similarly, you could look for beer and milk. So beer and milk together, they appear in 3 out of the 5. So it's 3 divided by 5, 0.6 or 60%. Right? Similarly, for beer, milk, and lemon, the support is 40%. So now, as I said, like as a data miner, you would define some threshold, the min sup. Let's say, for the purpose of our discussion, if the min sup was 50%, that you are saying that something would be frequent if only it has a support of 50%, or it's found in at least half of the shopping baskets. Then beer, the pattern beer, and the pattern beer and milk are both frequent based on this criteria. Okay? So this was just the simple frequency, right? So from simple frequency, we move to association rule. So association rule is like described as this, x with an arrow pointing from x to y, which means x is associated with y. Okay? Again, both x and y are item sets. And for an association rule, we define 2 terms. We define support, as earlier, and support is probability that a transaction contains both x and y. But now we define another term, confidence. So confidence is a conditional probability of y given x, right? So basically, it's the conditional probability that a transaction that contains x also contains y. Okay? So now, let's see a concrete example. So we saw the milk and beer frequent pattern. It has a support of 60%. Now, what about the association rule? Beer is associated with milk. What's the support? The support is the joint probability, P of x comma y, which is 60%, right? Which is just the simple support that it's in 3 out of 5 shopping baskets, so it's 60%. So now what's the confidence? So the confidence is 75%. So can anyone explain how we got that 75% number? Anyone? Yeah.
Did you say the transaction that contains beer?
Say that again?
If you consider the transaction that contains beer,
If you consider the transactions that contain beer, okay.
you found 3 out of 4 that contains milk. So it's
Okay, perfect. So yeah, so as we saw on the previous slide, it's the conditional probability that the transaction that contains x, so x is the denominator, it also contains y, right? So we are looking for the association from a beer to milk, right? So how many transactions contain beer? 4 of them, okay? Transactions 1, 2, 3, and 5. And how many of those transactions that contain beer also contain milk? So 3 of them, transactions 1, 2, and 3. So 3 divided by 4, 0.75 or 75%. Okay? So similarly, you could compute the association rule. Beer and milk are associated with lemons, right? So the shopping baskets that had beer and milk also had lemons. So the support for this rule, so you could see these 3 things together, that is the joint probability is 40%, right? Because they occur in 2 out of the 5 shopping baskets, in particular shopping basket number 2 and 3. And now what's the confidence of this association rule? So it's 66.7%. So we look at the shopping baskets that contain beer and milk. So how many of those are there? There are 3 of them, transactions 1, 2, and 3. And how many of them also contain lemons? Only 2 and 3. So 2 divided by 3, 66.7%. Okay? So now I want you guys to do a small calculation for me. So find the support and confidence for the association rule. Milk is associated with a lollipop. Okay, so milk arrow points to lollipop. So please compute the support and the confidence for that rule. Yeah, so I said milk comes first, then lollipop. Yeah, so milk, yeah. Okay, anyone? What's the support of this rule? 40%, yeah. And how about the confidence? Anyone? What's the confidence of the rule milk is associated with lollipop? Say that again? Yes, so it's 50%. So we look at how many transactions have milk, transactions 1, 2, 3, and 4. So 4 transactions, and how many of those also have lollipop, 2 and 4. So 2 divided by 4, 50%, right? Okay. So let's move ahead. So this was just like a toy example to motivate like how these things work. But frequent item sets and association rules are all around us, right? So I'm sure all of you, when you go to Amazon, you see things like such, where you say frequently bought together. You just put one of the books for a course in your shopping cart, and it says, oh, you might also want to buy these other 2 books because they are bought together, right? So those are nothing but frequent item sets, okay? Because frequent item sets that would surpass some threshold that Amazon might have had based on their like prior domain expertise in that area and what they might have seen in the past people might be purchasing. And then you also see association rules on Amazon, okay? Customers who bought this item also bought this, right? So you can see it's a conditional probability. You know, it's moving from the book that you have in your cart to all of these books, right? And so these are the most confident association rules. So it shows them in some order. I think it's most likely an unranked order. At least in my experience, that's what I have seen when I use Amazon to buy such things. Yeah, but you can see that these simple like frequency patterns and association rules, they are like very powerful, and like they like help us gain some information about associations and frequencies of the items. So now the question arises, how to find frequent item sets? I showed you a stylized, like a toy example where you could compute things by hand, but things might not be as simple when you have 1 billion items, right? And as we will see, it will soon become computationally intractable to compute some of these things in large data sets. So here's a brief pseudocode for doing that. So scan every transaction in database, enumerate the possible subsets, check whether their frequency is above the minimal support, and first find frequent item sets, then compute the confidence of those associations. Okay? So here is a simple algorithm for that. To get the frequency, we just need to count, right? And one would expect that counting is easy. However, like assume that you have 1,000 items in your, like 1,000 unique items in your database. How many 2-item subsets are there? So it's approximately 1,000 choose 2, right? And how many 3-item set subsets are there? It's close to 1 billion. So how do we quickly scan these 1 million or 1 billion items? And for 4 item sets, you could see like it's a combinatorial explosion. Like you would see many, many billion transactions. So how can we quickly sift through these item sets to find out the items that are most frequent? Okay. So a key property, which researchers came up with about in the 90s was this idea regarding the downward closure property, right? So just to remind, what we're trying to do here is that we have this really large collection of items, all possible 2 item sets or 3 item sets. We want to prune them somehow so that we don't need to consider or like in the terms of your Python code, you don't need to iterate through all the million items, right? Can we just iterate through a small subset of them to find the frequent item sets? So this property is called the downward closure property, and it essentially says that any subset of a frequent item set must also be frequent. Okay? So if milk, beer, and lemon are frequent, then so is beer and milk, right? And the reason for that is it's like self-explanatory that every transaction that has milk, beer, and lemon, it also contains milk and beer, right? So the number of times milk and beer occurs, it has to be at least as many times as milk, beer, and lemon occur. Okay? It cannot be less than that because it's a subset of it. Okay? So now, what does this imply? So this implies this has implications for this simple algorithm, a very, very popular algorithm for frequent item set mining called the a priori algorithm. Okay? So as I said, this algorithm was developed about 30 years ago, but it's a very, very popular algorithm. And based on a simple principle, if any item set is infrequent, none of its superset needs to be considered. Okay? And here's how the a priori algorithm works. So initially, you scan the database to get 1 frequent item sets. Then you generate k plus 1 candidate item sets from length k frequent item sets. Then you test the candidates against the database and terminate when no frequent or candidate set can be generated. So now let's run through an example to make things more concrete. Assume that the minimal support that you have specified is 2. And here is your database. So the first scan of the database will look for 1 item sets, right? That is just the raw counts of the different items. So you see beer, milk, watermelon, lollipop, lemon, and wine. Okay? So here are the counts of those. And we have a minimum support of 2. So as you can see, 2 items immediately drop off, the watermelon and wine. So both of them occur only once, so we just drop them. And so that means that the frequent 1 item sets are these 4 items, milk, beer, lollipop, and lemon. So then we make a second pass. So note that we only start with the frequent 1 item set. We do not go back to the original database. We start with the frequent 1 item set and generate the candidate 2 item sets. And how do we do that? We just do what's called a self-join, right? We consider all possible pairs. So so there are 4 frequent 1 item sets. So we consider all pairs of those frequent for all those 4 items. So it's 4 choose 2, and so there are 6 possibilities, right? So you can see milk and beer, milk and lollipop, and so on. And then once we've generated the candidates, we look at the database to see how many times they occur. So we make a second scan of the database. Okay? And now we consider these 6 possible items, 2 item sets. And once again, we count and see if they're greater than the minimal support. So it turns out, again, Most of them are except two. So beer and lollipop occurs only once, and lollipop and lemon also occurs once, so we throw them out. And then that means that our frequent two item sets are these four item sets, okay? So now what do? We once again generate candidates for three item sets by doing a self-join. Okay, so we get these three candidate items. So we get these three candidates for three item sets, as you can see. And once again, we do a third scan of the database to count the occurrences of these three item sets. And two of those three items fall out because they do not meet our minimal support threshold. And in the end, we're just left with one frequent three item set, which is beer, milk, and lemon, right? So in the end, we can see that here is the list of frequent one item sets, frequent two item sets, and frequent three item sets. Okay. So here is like the pseudocode for the a priori algorithm, right? So input is the database and the minimum support. What you do is, like, for k is equal to 1 till you get an empty set, you keep on generating the new candidates, and you increment the count if and look at candidates which have support greater than minimum support, right? So this is just a code version of what you saw, the process that you saw on the previous slides. Any questions? Yeah.
How to choose the optimal minimum support?
So as I said, so minimum support is a user-defined hyperparameter. So you would choose it, like it's just given to you. But if you are, like, let's say, working in some industry, like, you want to choose minimum support, it's just based on domain expertise, like what's a good number for that particular domain. So as I said, like, if you're working in a music store data, then it might be the minimum support number might be different, but for say a grocery store, it might be different. But it's given to you. So again, you don't want to have it too low because then everything would be frequent, right? But you don't want to have it too high also because then everything will be infrequent, right? Like, so then nothing would. So yeah, so it's like a, like a tunable parameter. Like, you try a few numbers and see, like, what gives you the most interesting things that you want to look at. Question? Oh, yeah.
Can the minimum support can be relative number, say top 5 or top 10 most frequent?
Yeah, that's a good question. Yeah, absolutely. I mean, you could define minimum support in that way, right? So right now, as you can see, that we are pruning stuff. We are removing things that do not meet the minimum support threshold. So in that case, you would only keep the top k items, that you said. Yeah, you could do that. Great. So now, what are some of the challenges? It's like a very simple algorithm. What are some of the challenges of a priori? So the first challenge is that it needs multiple scans of database. So each time you have to find like a given item set of size 1, 2, or 3, you have to make a scan of the database, right? So if you have to think about a really, really large database, like maybe if you are working at, I don't know, some sporting goods company or a grocery store, like think about how many items there are that if you have to find the collection where people purchase, 5 or 10 items. So in order to find item sets of that big size, you have to, how many scans of the database you have to make? Like you have to make 10 scans of database. And think about all the combinatorial explosion in considering all the subsets of that size. There are just so many possibilities, okay? But, like a saving grace is that though there are a huge number of candidates, most of them are not frequent, right? And there is the tedious workload of computing the frequency of every candidate, right? So for every candidate, we have to go through the database and see if they are frequent or not. Sorry. Okay, so since this algorithm is about 30 years old, I think it's highly likely that people have worked on improvements of a priori, and it turns out, yes, there are. Okay, so there are clever ways to implement some of these things that we just discussed. That we don't need to make multiple scans of database for each. For computing item set of each size, and that even if we make a scan of the database, we don't have to compute the frequency of every candidate, right? So there are some of these improvements that people have made. So to shrink the number of candidates, to do some sampling and approximation, that it would give you the most likely 3 item sets, or that with some probability that these item sets are the most frequent or the highest or the most confident, right? And then people have used techniques like MapReduce, which are basically you spawn lots of different jobs, and on each on different images of the data, and you aggregate the results. So distributed counting is like one way where people have sped these things up. And so there are several algorithms that incorporate many of these improvements. For the purpose of this class, they are too advanced material. So I would suggest you read this book, which is also in the list of readings, by Han, Cumber, and Pai. So chapters 6 and 7. So they would tell you some of the more advanced algorithms and that people have used for frequent item set mining, and how you can incorporate some of these sampling and approximation based techniques to get to scan through really large databases to do that. And also this is a chance for you guys also, if you think of a clever way to search through a database without enumerating everything, it's a chance to contribute to this literature, write a research paper, or file a patent for an algorithm. So so I highly recommend you to read through this. And it's some of these ideas in this chapter, they are very clever, right? They are very clever ways of accounting for things without going through the laborious task of enumerating everything that's there in the database. Okay, so now this was the a priori algorithm is about computing the frequent item sets. So now what next? Once we've computed the item sets, how do we evaluate these item sets? Okay, right? So now there was this question that how do we compute the minimum support? But even if there is some reasonable way to compute the minimum support for a given application, are all frequent patterns interesting, right? Would they all support decisions of the management or the data mining division at some company, right? So we need a way to evaluate what's still the true knowledge from the frequent patterns, right? So from frequent patterns were just raw data. So the database contains some raw data. From raw data, we have extracted some knowledge, right? But even that knowledge is, of course, more refined than the raw database, but still it needs more refinement. It might not be all the information that we might need to make business decisions in the data mining division of a company, right? So just recall what we studied in lecture 1, that data mining is a process of knowledge extraction. So we extracted some knowledge, but there's still a ways to go to use this knowledge to make decisions. And 2 common ways of evaluating item sets are what's called a max pattern and a closed pattern. So a closed pattern means that if X is frequent, then there exists no super pattern with the same support as X. Okay? And a max pattern means that X is frequent, and there exists no super pattern that is also frequent. Let's see an example. So here is our example from earlier. Beer and milk, turns out it's a closed pattern. So beer and milk has a support of 60%. Okay. And what was our definition of a closed pattern? Closed pattern means that there is no superset that has at least as much, like same or higher, support as X, right? So milk and beer has a support of 60%. There is no superset of milk and beer that has a support at least that. So milk, beer, and lemon has a support of 40%, which is lower than 60%. So hence, beer and milk is a closed pattern. And then milk, beer, and lemon is both a max pattern and a closed pattern. So first of all, let's see how it's a closed pattern. It's a closed pattern because there is no superset of milk, beer, and lemon that has at least as much support as that, like 3-item set, right? And it's a max pattern because there is no superset of milk, beer, and lemon that is also frequent. So it's both max and closed. So let's see why milk and beer is not a max pattern. Can anyone explain why milk and beer is only closed pattern but not a max pattern? Anyone?
The milk, beer, and lemon superset has an equal support as the minimum.
So for max pattern, so you're on the right track. So on the max pattern, we don't have to look at the support of the superset. We just have to look at whether it's frequent or not. So right, super pattern, that is also frequent. So beer and milk has a superset, milk, beer, and lemon, which is also frequent. And that's it. So that's what we need to ensure that it is not a max pattern, it is only closed. Yes?
Could it also be explained that there's the same percentage of lemon and beer?
There is the same?
Like milk and beer and lemon and beer.
Milk and beer and
Both 60%.
so milk and beer is 60%, yes.
And lemon and beer is also 60%.
Lemon and beer, but that's also a 2-item set, right? It's not a superset.
Oh, it's the
Superset is like it needs to have more items. So it cannot be a 2-item set. So superset, yeah, it would be at least 3 items. Okay? Okay, so now, so max and closed pattern are like one simple way to look at some interestingness in the association rules that we might have found. Now let's see, some other ways of doing association rule mining. So if we want to find, if we want to move from simple frequencies to association, right? So as we've seen, what we do is we find association of X with Y that has a high support and high confidence. And as we saw previously, support is just the joint probability of observing both X and Y, and confidence is the conditional probability, P of Y given X, right? And we denote like any association rule X from X to Y with its support and confidence. And what we do is we first find the frequent item sets and then check its confidence. So here were some association rules for recommendations, that I previously showed. Yeah, but we don't have to stop there. Like, association rules can also be used for classification, right? So think about a classification task where Y can be some class label, for example, whether an email is spam or not. And X could be a URL or could be an image, and you want to classify whether a URL and an image is associated with spam. So what's the support of this association rule? So let's say the support is 1% of all emails. 1% of all emails contain a URL, an image, and spam, and the confidence is 90%. 90% of emails that have this URL and this image are spam, right? So, and then we could come up with this rule that classify as spam if X appears in email. So now you can see that in other courses you guys would study classification algorithms, like logistic regression or support vector machines or random forests and so on. That there are simple association rules also that could help you come up with rules to classify things. Okay, so you could just use support and confidence to come up with a simple rule to describe like whether they have a certain label or not. And in this case, it was spam. And you can even go one step further, right? So this is just one rule. And what if you have multiple rules? So then you could combine with some of the techniques that you learn in your machine learning class. So for example, you could do like an ensemble of these features by using something like boosting or bagging or like even random forest type things, like where you maybe you could have some kind of voting mechanism where each association rule could vote like on how important it is to a given classification rule, and you learn like what should be the weight of each of the rules in deciding the outcome. Okay, so there are like association rule mining is very, very simple thing, but it has like lots of application, as you can see. Like you could make far more complex things based on these simple these simple rule mining. Okay, before we proceed further, are there any questions? Okay. Okay, so and we don't have to stop there. Like we could like represent. We could even use these frequent patterns, for classification, other than what I described on the previous slide. Here, what we are saying is that we could use these association rules to come up with features. We could come up with features in like that, or the X's that you put in your machine learning algorithm, right? So the features could be either the individual items, or it could be the frequent patterns or associations, and then apply any classification algorithm. So a canonical example of this is, let's say you have, like there are research papers that you have to classify whether they belong to data science or to biology. And a simple approach which you might study in your a machine learning class would be what's called a bag of words classifier, right? So bag of words classifier is that you take all the words in a given document and then use those words to classify what that document is about. So here we are saying that rather than using all the words, that you could even use like some smaller subset of that, just the frequent patterns, right? And in the parlance of this document classification task, like these are called the 2 grams or 3 grams or n-grams, basically n-gram classification, right? So an n-gram is nothing but like an item set. So for those of you who have taken natural language processing, or you will, so you would hear this term maybe in the first lecture there, like it's an n-gram of words. So n-gram is just an item set of or item set of words. And you could use that as features in any classification algorithm. Okay? Okay, so now we've seen some of the ways to classify, how like some of the rules, like some of the frequency, like some of the frequent patterns would be like worth looking at. But like let's delve more into how how do we know if some of the associations are really interesting, or how we could we make decisions based on some of those associations, or if not, like how do we come up with more sophisticated associations that could be used for finding interesting patterns. So now, like whatever we've studied for the last half an hour, based on this, if I have to make an association rule, and I'm working at a video like a video game store, like let's say Best Buy, that we could say customers who buy computer games, they also buy videos, right? And the support of this rule is 40%, and the confidence is 66.7%. However, these numbers could be misleading, right? Because we don't have a baseline number. We don't have the base rates. So what if the probability of buying videos is 75%, right? So any person who goes to that video store, let's say Best Buy, 75% of them buy videos. And here we are saying people who buy computer games also buy videos. 66.7% of people who buy computer games also buy videos, to be more precise. We think, wow, it's a high number, but it might not be, right? Because 3/4 of the people, 75% of people buy videos regardless, whether they buy computer games or not, okay? So what's happening here? And now let's think about like a converse pattern, right? So basically like a complement of this. Let's think about an association rule, people who buy computer games and not buy videos. So, and it turns out the support of that rule is 20%, and the confidence is 33.3%. So it's more accurate because it's containing more information, but it has lower support and confidence. Okay. So, so as you can see, from both these examples, what we are seeing is that some of these rules could be misleading, but others that might not be misleading, they might not have enough support and confidence, right? So they might not even catch our attention because they would not pass our threshold in the first place. So a potential solution to this problem is to measure correlations instead of conditional probabilities, okay? And let's see once again with a concrete example. So we construct what's called a two-way contingency table, which looks like this. Okay. So each cell in this table shows how many people buy video games and videos and games, videos and not games, right? So all the 2x2 possibilities. Okay. And there are a total of 10,000 transactions here. So now we instead of using conditional probability, we use some interestingness measure, and the one that we will see here is lift, and as I will show in the next few slides, there are many, many others that people commonly use. So lift is one of the most common ones that you will see used in industry. So what is lift? So lift is just the ratio of conditional probability and the marginal probability of y, right? So the marginal probability of y was, when I said that 75%, what's the overall probability of buying 75%? So basically, that's just P of y, right? So that's what we are dividing by here in the lift. So the top is just the confidence, and we divide by the probability of y. And we could use Bayes' rule to factorize this conditional probability into joint probability of P of x comma y divided by P of x, and then P of y is already there. So the lift is the joint probability of P of x comma y divided by the marginal probability of P of x and marginal probability of y, P of y. So now let's compute the lift of the association rule games and videos. Okay, so what's the numerator here? So the numerator is P of x comma y. So we look at this 2 by 2 contingency table, and we look at videos and games. So it's 4,000. Okay, so 4,000 divided by 10,000. We have to compute the probability. And in the denominator, it's P of x. What is x? X is games. So if you have to look at x, how many people buy games? So it would be the sum of people who buy games and videos and people who buy games and not videos. So it's 4,000 plus 2,000. That's 6,000. Okay? And once again, we divide by 10,000. And then second one is in the denominator, the second term of denominator is P of y. P of y is the probability of videos. So how many people who buy videos? That's the sum of people who buy videos and games, and sum of people who buy videos and not games. So it's 4,000 plus 3,500, 7,500 divided by 10,000. Okay, you compute this number. It turns out it's 0.89, and you could also compute the lift, like the lift of the complement of this games and not videos. So the lift of that is higher, right? So the lift of games and not videos is higher. It's 1.33. It shows that it's a more interesting pattern that we should base our decisions on than like simple games and videos, right? And this captures the intuition, what we saw 2 slides earlier, that we are not controlling for the base rates, that people were going to the store and they were purchasing games, they were purchasing videos, like 75% of them were doing that, and we were not taking that into account. So what we can do is, we could look at all association patterns in our data, compute their lifts and rank them by lifts, and look at some of the top 5 or so and think these are the most interesting patterns. Okay, so does this make sense to everybody? Any questions? Yeah, okay.
Yeah, like intuitively, how does this lift number quantify like interestingness?
Yeah, so I think so that's a good question. So we will see some other interestingness measures that could quantify these things more precisely. But over here, you could just look at the magnitude and then rank them based on that magnitude.
Magnitude, so like this is bottom one, 1.334.
Yes. So that one has a higher lift, and you could, if there was another rule like not games and not videos, like you could compute its lift also and see the thing with the topmost, like the highest magnitude of lift, and that would be the most interesting pattern. But I totally understand your point that what does 1.33 mean? Like, is it some tangible number that we could interpret? It's just a relative magnitude.
Okay.
Yeah. Okay. So another interestingness measure is this chi-squared hypothesis test, right? So this is a hypothesis test that you might have seen in your stats class. It's used to measure whether 2 variables are independent or not. Okay. And this is computed this simple calculation that we compute the observed count of a cell and the expected count of the cell. We square it and divide by the expected number. Okay. So the expected count, and how do we compute the expected count? So the expected count is the row total multiplied by column total divided by sample size. And then, as with all statistical tests, we compare the value that we would get out of it to like a table of critical values of the chi-squared statistic, and then we could get a confidence interval, whether this number is significant at 95% confidence or 99% confidence and so on. And if it is, then you rest assured that this is a significant pattern, right? So this addresses some of the issues with the question that was just asked, that in this case, that there is a confidence interval, like there is a confidence level that you could associate with the rule. So it would automatically tell you whether something is significant or not, right? So you don't have to worry about whether a number 100.7, a chi-squared statistic of 100.7 versus 95.4, which of them is more significant. Like, you could tabulate them and see how they compare to confidence level, and if they like fall into one of those buckets, like 95% confidence or 99%, that some of the numbers that are commonly used by statisticians to define significance level, then you could say that this is an interesting pattern. Okay. Okay. So now let's go through this exercise and compute the chi-squared statistic. So we have the same 2x2 contingency table. So the values in the parentheses are the expected numbers, right? So the chi-squared statistic is nothing but, as we saw here, observed minus expected squared divided by expected. So you can do this math. I mean, like, it's a simple calculation. And you would get this number 555.6 in this case. That is, we would say that the chi-squared statistic for this is 555.6, and then you would compare it to some critical values of the chi-squared distribution to see whether it's significant at a 95 or 99% level. And if it is, then you could conclude that this is an interesting pattern. Okay. Now, we don't have to stop there. Turns out that there are lots of other interestingness measures. So we saw two of them. Right. So let's see. So we have support here. We have confidence here. Yeah. So somehow this table does not have, it does not have the chi-squared. I think this might be like an abridged version of that table. But yeah, so interestingness and lift are, chi-squared statistic and lift are definitely two of the more interesting ones. But there are lots of other ones, there are lots of other ones that you can see. So actually, lift is what they're calling interest here, right? So if you see interest, number 14, it is a probability of A comma B, the joint probability divided by PA and PB. So that's exactly what it is, right? So yeah, so long story short, like, you could see that there are lots of ways to compute interestingness, right? And all of these measures have some advantages or disadvantages of over the other. And you could read this paper to read more about them, and they're all very simple to calculate. Like, you could like 2 lines of code in Python should be able to do that. It could be a good exercise to compute these for some sample database and see what interesting insights you could get, like based on like whether something would be a significant pattern based on one interestingness measure, but not on other, and what implications does it have about the insights that you can get from that data. Okay, so another interestingness measure that's also mentioned in this table, then that I really want to cover, and it is because it's a very, very important concept, useful for any kind of data science, data mining application, is this idea of mutual information, right? So it comes from this whole idea of information theory, okay? So mutual information, it measures mutual dependence between 2 random variables, right? And information theoretically, you could define it as it's the amount of information about X through observing Y. Okay? So if you observe Y, what does it tell you about X? And if those variables are independent, then of course it will tell you nothing. The mutual information would be 0. But if they are correlated, then there will be some mutual information. Right? So now you could see how we could use mutual information to compute interestingness. How much does the fact that somebody bought videos, somebody bought games, also bought videos, tell you, sorry, somebody who bought games tell you about them buying videos. Okay, if it is really high, then it could be an interesting thing, that. But if it's a mundane pattern that almost 75-80% of the people are doing both these things, then it's not an interesting thing. You could just look at other more interesting patterns. Okay, so here's how the full mutual information is computed. Okay, so X and Y are the random variables, and in this simple case of appearance of an item, they are either 0 or 1, right? So they're binary random variables. So the formula for mutual information is p log, so p log p over the pxy log p of xy divided by the marginal probabilities p of x and p of y, right? So that's what exactly we are doing here. So basically, we sum over all the possible values of x and y, and we compute the joint probability that p of x is equal to x, comma y is equal to y, and then we take the same number in the numerator inside the log and divide by the marginal probabilities, right? So now the question arises: why this form? Why this formula? Why not why not flipping the numerator to the denominator or vice versa? Well, because this is how mutual information is defined. You should read an information theory book or read some of Claude Shannon's papers to see why they define mutual information like this, right? But this is the definition of mutual information, okay? So now let's compute mutual information for the cases that we are interested in. So let's compute for the association rule games and video. Okay. So now, as I said, x and y are random variables, and they take two values in our case, right? Either they are present or they are not. So what that means is that there are four possibilities. So games and videos, games and not videos, not games and videos, and not games, not videos. So for all these four possibilities, you could one of these terms would contribute, this term would have four values, right? Because we are summing over x and y, and there are two values of x and two values of y, so four values in total, okay? So we sum over all the four values, right? And that's the total mutual information. So now let's see a couple of these numbers and how do we get there. So the 0.4, so video and games. So videos and games is 4,000 divided by 10,000, that's 0.4. And then log p of x comma y, it's again 0.4. Now you divide it by probability of just games, that's 4,000 plus 2,000, right? You just sum over, that's the sum of the first column, so 0.6. And then the sum of the first row is just the people who purchased videos, that's 7,500, so it's 0.75. So that's how you get the first term. For the second term, so it's probability of games and not videos. So let's go to that cell in this 2x2 contingency table. So games and not videos is this number, 2,000, right? So 2,000 divided by 10,000, that's 0.2, and that's what we also have in the numerator. In the denominator, we once again have, we have P of games. P of games is the sum of first column, so it's 4,000 plus 2,000, 6,000, that's 0.6. And the second is probability of not videos. So probability of not videos is the second row. So it's 2,000 plus 500, 2,500 divided by 10,000, 0.25. Okay. So similarly, you could compute the other two values and you just add them all up. That's the mutual information. And in this case, it comes out to be 0.04, right? So once again, just as we saw with Lyft, it might not be an easily interpretable number, like what does 0.04 mean? But what you could do is you could compute mutual information of many rules and rank those different items based on their mutual information, and the rules that would be higher would be more interesting than the ones that would be lower. Okay, so this was I would say the full mutual information. But another thing which is used a lot in mutual information literature is this idea of point-wise mutual information. So point-wise mutual information, it means that rather than caring about all the 4 configurations, 2 values of x and 2 values of y, we just care about one value, one configuration, one value of x and y. Okay, and that should be from here you could see that rather than doing all the 4 values, we just compute one value. Right, one particular value of x and y. If we have to compute the mutual information between video and games, we could just compute it like this. Right? So let's say if we have to compute the point-wise mutual information between games and videos, what we saw here, it would come out to be minus 0.17. Right? And games and not videos, it would come out to be 0.42. And once again, you could rank things based on the magnitude. So over here, you could see that games and not videos, even by this measure, it has more mutual information. So somebody not buying video games, not buying videos tells you more about them not buying than buying games, right? So even by this, this is a more interesting, even by this metric, it's a more interesting measure, more interesting association rule. Okay, yeah.
So these measures are only meaningful when compared to the same measure from the same set, right?
Say that again.
They're only meaningful relative to the other interestingness measures within the same item set, right?
Can you give an example?
You couldn't. 0.42 only is meaningful within this particular games and videos.
Of course. Because, so it's about those 2 random variables, right? The random variables in this case are the games and videos. You cannot use it for the shopping basket.
Right, okay.
Right? Yeah. So, of course, we are comparing only within that thing, right? And as I said, some of these do not have a, you don't know whether 0.42 is high or low, right? But what we can do is we could rank things based on the magnitude, right? That's what we can do.
It's only meaningful relative to...
Yes. Yeah, so now the reason that I covered mutual information is because mutual information, has been used a lot in other applications, where there might be item sets. Okay, so especially for text mining or natural language processing, people have used mutual information a lot to learn word representations, right? So as I said, for the text example, we consider words as items or the bag of words, and co-occurrence of words indicate semantic relationship. Okay, so the fact that the word new often occurs is often followed by York, it tells you that this might be a proper noun or an entity that might be interesting, right? So you can look at similar kind of patterns in text data. And in early 90s, people used these mutual information-based measures for natural language processing and text mining, and they are some of the best approaches. Even now, if you were to use them, they would perform as well as the state-of-the-art approaches, some of the deep learning methods that we have now. Okay, so mutual information, long story short, is a very, very powerful, a powerful technique to know about, right? It tells you a lot about the information shared between 2 random variables. Okay, so there's this famous paper by Ken Church and Hanks in 1990, so 33 years old. I think most of you wouldn't have been born then. Okay, so but this is like a very, very seminal paper in natural language processing in the early days of NLP. But as I said, like it's still used. People still use these things even today. So what we are teaching here is not something that is no longer relevant, right? So these things are still used a lot in text mining type applications. So what they did was they wanted to find some interesting associations with doctor in the 1987 Associated Press corpus. Okay, and N is 15 million. So 15 million words were in the 1987 AP corpus. So they compute the mutual information, right? So you could see what are the terms that have the highest mutual information with doctor, right? So it's honorary, doctors, and then examined, doctors, and so on. So now some uninteresting associations with doctor. So it's doctor with a small d, because doctor is always with a capital D, right? And then some of the common words like a or is. So now what I just said is something very, very important. So you can see a and is. So what are these? So prepositions, as you know, in text, they occur all the time, right? So if you were to do text processing, like what are some of the common things that you would see? You would see determiners, prepositions, that they would occur like 80% of the words would be these things. And 20% would actually be useful words that would tell you what's happening in the text, right? So now based on mutual information, it's able to figure out that a or is not interesting, that it's not a common association with doctor, because a and is occur with pretty much every other word, right? Even if instead of a doctor it was a nurse or a person or an actor, you could maybe not an actor because then it would be an, but player. Okay, so it would still occur. So that's why a doctor is not an interesting association. Similar idea to what we saw in our like games and video example, right? So that's why like mutual information is a very, very simple method, but it's like very, very important. Like you could, in fact, if of all these techniques, if I were to say, if I was working at a company and they would ask me to use some method to find interestingness, mutual information would be the first one that I would go to, because like it's been tried and tested for like many decades in many different applications, and it just works remarkably well, right? And I'm sure these are just a couple of examples, like text and like other item sets are the common examples, but there could be other examples in like biology or medical applications where the items might be something else, right? And once again, you could find mutual information between different things, and it would give you, some, like I would say, highly non-trivial insights into what's happening. Okay, so more applications in text mining, right? So you could do spell check. Again, spell check would be to like figure out whether something is associated with something, right? If like you have a missing, like you spell, let's say a word player with you misspell PLAIR or something like that, right? So because that word would never occur in the corpus because it's misspelled, so its mutual information with the other words would be lower. So you could spot out the outlier in this case. You could also look at polysemy. Polysemy is like means that one words with multiple meanings. There's a very important problem in text mining called word sense disambiguation. So when I use the word bank, does it mean river bank, or does it mean Bank of America, or like some kind of financial institution? Okay, just one example. So how to figure out, and now you can see the correlation patterns or the mutual information of the word bank in the two senses that I just gave. It would be quite different. Okay. to find synonyms, phrase detection, entity extraction, word clustering, and so on. So there are lots of applications of this simple mutual information rule. However, look, what we are trying to find here is just correlations. Okay, so there is nothing causative about what we are seeing. Okay, and you see see examples of this type, floated around, that ice cream sales is correlated with the rates of drowning, but no real causation between the two. Okay, so there are lots of these memes online where people say, that that here is a pattern of the number of ice creams that people have purchased each year and the number of deaths by drowning. And then they would show that there is a positive correlation of 0.4 between two, which means that eating ice creams can cause drowning, right? But we all know that, so in causal inference, a common thing that causal inference is different from predictive inference that you learn in machine learning or in this class is that there are confounders, right? So confounders are like a common variable that affects both the things, right? So in this case, the causative statement that somebody is making is ice cream sales causing deaths, drowning deaths, right? However, there is a confounder here. A confounder is a variable that impacts both ice cream sales and deaths. And if you control for that confounder in some regression, the correlation between ice cream sales and drowning deaths would go away. So can anyone guess what the confounder would be for this example? Something that is correlated with both ice cream sales and with drowning deaths? Yeah? Yeah, warm weather or summer, right? So summer affects ice cream sales, high sales in summer. And in summer, people go to the pool, so there are not lots of, but some people drown, right? So, okay. So what are some of the open questions in item set mining? How to make some of these things, such as a priori algorithm, efficient and scalable, okay? And how do we? So second thing is, how do we extract patterns with certain constraints? Okay, so the constraints can be significant patterns instead of frequent patterns. Frequency is just one way of looking at importance, but there could be other ways of thinking about importance of patterns. How do we interpret patterns? How do we evaluate interestingness measures, right? So that's what I said. It could be an interesting project if somebody wants to do that. There are these 20 interestingness measures in that table. How do we know which one is the best? I mean, I'm sure, I don't think that there is anyone that's best, but in what circumstances would you prefer one versus the other, and what applications would you want to use one versus the other? It's a very interesting empirical exercise, if somebody wants to do that. And how do we use item set patterns for classification? I gave some ways to do that, how to blend the different features into some kind of classifier, or how to use simple association rules to do classification. But there could be more possibilities there. And again, there are lots of applications. So text and grocery stores and any kind of say. Discrete items are examples that I gave, but there are many more items. I'm sure there are lots of applications in biology and bioinformatics where there are discrete items and you care about their presence or absence, the DNA nucleotide values, or the gene expression levels. So how we could use some of these techniques in those applications. Okay. So here are some of the tools for frequent item set mining. So there's a classic package in Java called Weka, but more recently, people have been using this package called ML extend. So it has some useful frequent pattern mining functionalities, and it's very useful. So for homework 1, we would be using ML extend. So you will use some of the functions from there, but then we would also ask you to implement some of the other approaches that are not that are there, but we want you to look under the hood and implement them yourself. Okay. So what you should know, so the basic methods of frequent pattern mining. So we've only looked at patterns. Okay. So we will look at similarities in the next few slides. Okay. And how a priori is able to scale up frequent pattern mining, how to measure interestingness, applications of item set mining, and co-occurrence is the key in text mining. Okay. So before we proceed to similarity-based item set mining, are there any questions? Anyone? Okay. So the first 3/4 of today's lecture was about pattern finding in item sets, right? But then similarity is the other way to look at like data mining functionalities, right? And similarity is a measure of how much two data objects are like, and it's the converse of distance. You know, high similarity, low distance, and vice versa. So now, how can we look at how can we do similarity-based item set mining? Okay, so natural question to ask is: are transactions T2 and T3 more similar than T2 and T4? So what's the intuition here? Two sets are similar if they share a lot of items. Okay. However, we also know that the larger the set, that just the sheer probability that it will share common items with other sets. Okay. So we want to look at sets that share similar items, but we also want to discount or control for the fact that the larger sets are more likely to share more items with others. So intersection and union, two set operations, as I'm sure all of you know. So intersection is the largest common subset of A and B, and union is the smallest common superset of A and B. So here is the intersection of these two, of beer milk and watermelon, and milk beer and lemon. So what's the common in these two sets is beer and milk, right? And what's the union of these two item sets? So it's just the collection of the common superset, it's the smallest common superset, right? So it would be like beer, milk, watermelon, and lemon. Okay. So based on this, we come up with this measure of similarity of two sets, also known as the Jacquard index. So what's the Jacquard index? It's the number of items in the intersection divided by number of items in the union. Okay. And Jacquard distance is conversely 1 minus the Jacquard similarity. So properties of Jacquard similarity, you know, it's a symmetric. Similarity between A and B is the same as between B and A. It lies between 0 and 1. Similarity is 0 if they share no items, and similarity is 1 if the two sets are identical. So now let's compute Jacquard similarity. So here are transactions T1 and T2. So T1 and T2, what is the intersection of transactions T1 and T2? So it's milk and beer, right? So that's the intersection. And what's the union? So T1 and T2, so T1 has 3 items, and T2 has 4 items. But if you look at the union of them, there are 2 repeated items, milk and beer. So we look at the union of them, there are 5 total items. So 2 divided by 5, 0.4. Similarly, between T2 and T3, the Jacquard similarity is 0.75. Okay. So can you calculate the Jacquard similarity between T2 and T4? Give you a minute. So how many of you have seen Jacquard similarity in some other class or some other way before? Can you raise your hands? Okay. So which class have you seen it? Anyone? Say that again? I see. So 650. So the SI is 650, right? Did you take it? So are you in the MSI program? Okay, okay. So typically most people, like at least in the School of Information, they take 650 and 671 in the same semester. But I guess in the data science program, you could take them in different years, which would cause this. Yeah. Yeah. So okay. So what is the Jacquard similarity between T2 and T4? Anyone?
0.5.
Yeah. So 0.5. So could you tell us what's the intersection? What's the numerator and denominator? What's the?
It's 2 over 4.
Yeah. So 2 over 4. So there are two items in the intersection. Milk and lollipop, and 4 in the union. Basically, all of T2 is in the union. So 2 divided by 4 is the Jacquard similarity. So now, interestingly, one thing that you should note is Jacquard similarity, although we've covered in the second half, like in the similarity-based interesting measures, Jacquard similarity was here too, right? So look at number 20. So yeah, it was just like a minor point, but. Okay. So so what we've seen on the previous slide was we computed the similarity of the shopping baskets, right? But we could transpose the original problem and compute the similarity of items, right? The similarity of items would be something that would be even more interesting. Okay. So what we could do is we could transpose this, like think of it as a matrix that you're transposing. So now you could see beer. Beer is in transactions T1, T2, T3, and T5, and so on. Like watermelon isn't just in one of them, and like wine is also in one of them, and so on. Okay. And once again, you could compute the similarity between milk and beer. So milk occurs in 3 baskets, and they both occur in 3 baskets, and like the union is all 5, so it's 0.6. So the similarity between milk and beer is 0.6. And of course, this is not making any general statements about the state of the world. It's only about that particular database or data set that you're analyzing, right? So if you analyze data from a different database, like it's very possible that the purchase patterns could be different. And similarly, Jacquard similarity between beer and lemon is 0.75. Okay, so and just as we saw for the pattern-based data mining, we could use similarity-based item set mining also for complex data mining tasks. Okay, we have 2 papers. We compute the similarity of them based on, like we could use even Jacquard similarity to compute similarity between them, or we could use cosine similarity or like other similarity measures between the 2 papers, and then we could use that for clustering, classification, ranking, and recommendation. Okay, so now what we've seen in today's lecture is like 2 different ways, 2 different sets of complementary set of approaches to look at item sets and what kind of patterns or similarities we could find between the different item sets. Okay. What are some applications of item set similarity? Similarity of text. Okay. Plagiarism detection. So many of my colleagues, whose assignments have lots of like writing-based homeworks every week, and there's a big risk of people using ChatGPT or these technologies. So they are using some of these techniques to find similarity of text, right? So you could use, like at the bare minimum, like you could use like a cosine similarity between these two things, or there are more sophisticated approaches, but like such kind of item set similarity approaches could be used for detecting similarity of text. Similarity of shopping baskets, customer profiling, right? People who purchase similar type of items, they might be similar. So you could recommend similar items to them on Amazon, or you could recommend them similar movies on Netflix. And we don't have to stop at just these examples, but also like you could also look at networks, right? Like if you have a social network, you could see people who have lots of common friends. That would be like their friend lists are similar. It's a very good chance that they also know each other. And then like on Facebook, as you guys know, that there is this, I think there used to be people you may know option where they would recommend you to connect to somebody on Facebook. So all those things could be based on similarity of friend lists. Okay, so what you should know, so how to measure the similarity between item sets, how to calculate the Jacquard similarity, right? So Jacquard similarity is just one way of computing similarity, but there are other similarity measures too, okay? And then how to use item set similarity for complex data mining tasks and real applications. And this is where the real innovation could happen. For some of you who want to do some projects, might want to use these ideas in your projects, for the final projects. Like think about how you could use some of these simple ideas for some application that you care about, that you might have been working on your previous job, or like your or your research and so on. Okay, so this was the last slide. So any questions? So item sets, I would say, are like on the surface, they might seem very simple, but there are lots of nuances in the way you implement these algorithms, like the a priori algorithm, the way you do pruning, the way you combine these things. So I highly encourage you to read some of these things that I mentioned in the slides about more advanced versions of the a priori algorithm, and also like get started on the homework. So in the homework, we ask you to compute many of these things, like compute mutual information, like implement some part of the a priori algorithm, and we have a similar emoji type data set that we ask you to work on. So yeah, so I think so these things are very, very simple but very powerful. Okay, so it's whatever we studied today. You might think, oh, these papers are written in 1990s, so they would be really, really old and nobody uses them. I think that cannot be farther away from truth. So these things are very, very simple, but the fact that we are teaching them in a class means that they are still highly relevant, right? Especially these ideas about mutual information, they are used in some of the papers that I recently reviewed for a conference, okay? So yeah, so it's good to internalize these things well and understand them. That would help you be an excellent data miner. Okay. Okay. So if there are no more questions, so I want to give you guys extra time to go to your discussion labs for those of you who have it right after the class. So I've been told by the GSIs at our weekly meeting that in some of the discussion labs, like only 5-7 students show up. So I think, like I've said it so many times, I think it's very, very important for you to come to the discussion labs. If you are not, like you are missing on important stuff. And let me tell you, based on the lecture, you might say, oh yeah, I've covered this in another class, I've done this and that. The midterm is gonna be hard, right? So it's, again, I'm not trying to scare you, but in the hard in the sense that those questions would really, really make you think deeply, right? By hard, it doesn't mean that we would have material that you haven't seen, okay? So you would have seen all the material, but they would really, really, like you will have to dig deep. And if you come to the class, which I mean, of course, all of you are, but also to discussion labs, in previous years, we've seen like those are the people who do well on the midterm and the final exam. So I highly recommend for those of you or your friends who might not be attending the discussion labs. So please encourage them to do that, right? Because the exams are, I think, about 50% of the course grade of the entire class. So, and we have our first exam, which is the midterm, on 11th of October, so less than a month from now. Okay, so please, come to class. This is where most of the learning will happen, and you will learn these things that would be useful for you later on. Okay. Awesome. So I'll see you guys next week, and I have my office hours as usual on Wednesdays. So feel free to come to the office hours if you have any questions. All the slides are already online.